My name is Valerie. I am a postdoc at Stanford University, and I'm going to take us even a little further afield. I'm a disease ecologist, so I'll be speaking to you today about the optimal deployment of genetic biocontrol under environmental uncertainty. Another thing I could have called this is JUMP for disease ecology. So first, what is genetic biocontrol? So it's a form of biological control or biocontrol, and that's when we're using living organisms to control the dynamics of an unwanted population. So one historic example is using foxes to regulate rabbits, so that produces the predator-prey dynamics in the Slotka-Volterra model that's on the screen. But genetic biocontrol is a subset of approaches that either alter the genes of species directly or they change the expression of certain traits. So there are many ways to affect these changes in practice, including genetic modification, radiation, or the artificial introduction of microorganisms, so that's just infecting something with a bacteria. And today I'll be talking about this as a form of public health intervention to prevent the spread of disease by mosquitoes. And there's two ways generally that this control can be implemented. Either a replacement, so we're substituting the disease-competent population with one that can't cause harm. And what happens here is, if you follow the green line on the screen, as the organisms that have been modified are released into the environment and they multiply, then we see the population of concern descending. Another form is suppression, and this is when we're reducing or removing the wild population of concern. With the same method, we release the modified organisms, and then we see the population of concern crashing. And the reason we would want to do any of this is that mosquitoes are often billed as the deadliest animal in the world. And so they're responsible for a lot of human suffering. Dengue is transmitted by the Aedes aegypti mosquito that's shown there. And it causes nearly 400 million symptomatic infections each year across 125 countries with an estimated cost of nearly $9 billion US globally. So the problem is already quite large, but it's also evolving. Mosquitoes are increasingly growing resistant to insecticides, and we also have growing human health risks thanks to a shifting climate, a warming climate. So why does climate warming matter? Well, biologists know that temperature is a primary driver of vector-borne transmission, including from mosquitoes. So the image on the screen there is one of something called thermal performance curves, and it reflects basically the optimum temperature for disease transmission by different mosquito species. And I just want to draw your attention to the sort of the rightmost curve there, where dengue transmission by Aedes aegypti is peaking at 29 degrees Celsius. So the bad news here, as the world gets warmer, it'll be favoring the increase of dengue in a lot of places that currently does not have it or has less of it. Okay, so the optimal deployment part. So genetic biocontrol interventions are essentially planning problems, and so we can abstract out from the domain specificity that I'm talking about here in public health and generalize them as a sequence of decisions, like the pink arrows in this illustration. So once we've chosen which technological tool that we're using, whether we're conducting a replacement or a suppression, we make a series of decisions about the timing and the frequency with which we deploy that tool. And then we decide spatially, where we're going to intervene, how many organisms we're going to use per release location. So each of these decisions, so they're collectively, as we know here, called a strategy or a policy that impacts the dynamics of the mosquitoes that we're targeting. And so we use field experiments and also laboratory experiments to collect data about that population response. And the goal here is to progressively improve our decision-making process. But my work has considered how we're making those operational decisions and asks whether we can improve that process using optimization. This is actually novel in this area because the subdiscipline of genetic biocontrol overwhelmingly uses mathematical modeling to predict outcomes rather than prescribe them. And by that I mean that they tend to develop models that forecast or characterize population dynamics under different assumptions of current and future situations. Another thing that they do is conduct a kind of a brute force exploration of different intervention decisions. So they're iteratively simulating choices within a predetermined set of options. There are also a handful of examples wherein optimal control is applied to optimize that strategic implementation of the decisions. However, the strategies that are derived using this have limited operational significance because the biological systems are quite complex, and incorporating the multiple dimensions of information that are necessary to prescribe the action can quickly prohibit obtaining a closed-form solution. So in part, when I was conducting my doctoral work, it was kind of introducing the field of genetic biocontrol to numerical optimization and consequently to JUMP. And so I kind of was trying to explain this as an instrument in our mathematical toolbox, and I would use this kind of basic illustration as a visual explanation of what I meant by constrained optimization. So I would give examples of relevant constraints in these areas as potentially the network structure of the geography over the population was living, and that dictates the spatial spread of either the vectors themselves or the modified organisms that we're deploying to control them. Another example is the species-specific environmental response of those mosquitoes. So we've just seen in those thermal optimums that there are temperature ranges outside of which they can't survive and at which they sort of are more effective disease vectors. So I explain how together those constraints create the solution space to our problem for an approach that's better suited to edge cases than simply the current one of iterating over a bunch of predetermined options. And this fact becomes more important as, thanks to an array of anthropogenic changes, of which I'll discuss a couple, past experiences are no longer setting reliable precedents for the future. So our empirical work is not proving to be as good of a guide. And then I illustrate in these explanations how the optimal solution can take the form of a time series. So this is our strategy or policy of recommended deployment times, sizes, and locations. One paper that resulted from this work was published in the SciM Journal on Applied Mathematics. So there I formulate models in which I consider the constraints that we've just talked about. So the temperature of a potential release location, the responsiveness of the disease vector of interest in that location, and then the network structure of the vector population there in terms of its geographic connectedness. A fourth aspect is the various approaches to genetic biocontrol that are either the technologies that are being deployed right now or being developed in the laboratory themselves have unique biological dynamics that need to be accounted for. So in that paper, I attempt to minimize a disease-competent population of those Aedes aegypti mosquitoes that I mentioned earlier, while also minimizing the cost of doing so. So this is a very small sample that I'm going to show you of the outputs of those optimizations in the form of a schedule of recommended deployments for the three of the tools that were tested. One of them is a suppression technology, 2 different technologies that use a replacement approach, and I'm happy to talk about the biological details if anyone's interested. But these images each have a release size, so the number of the modified organisms on the y-axis, and then time over a year on the x-axis. And you can see, even with a cursory look, qualitatively, that the frequency and the timing and the size that are prescribed by the optimization is quite distinct for each intervention when applied under the same conditions, the same organisms, the same conditions of environmental temperature and network structure. And these kinds of results can become important information to augment our empirical observations and guide intervention design decisions. But they also kind of highlight that it's quite low-hanging fruit in this domain area, is attainable via numerical optimization, and specifically through JUMP. So others have sort of described this algebraic modeling language that we're here to celebrate this weekend. And it makes it extremely straightforward to, the fact that it makes it extremely straightforward to prototype and explore different research questions in this space, even for, as I initially was when I began this, a novice. So ease of installation is another comment in the same spirit. When you're trying to convince your advisor that a research question should be explored using a mathematical method that he doesn't know and is technically new in your field, it helps enormously that in the Julia way of saying things, the tools just work. So for the example, that the fact that the solvers are automatically installed. From the debugging perspective, these models quickly became relatively large, acknowledging that there are different definitions of large. I'm talking about hundreds of thousands of variables and constraints. So it became important, for example, to be able to interface with the MI backend when debugging. And neither last nor least is the solver independence and the facility of kind of exploring different problem classes that was permitted by that. So in this work, I developed both nonlinear program and mixed integer linear program formulations of the genetic biocontrol problem. So as a result, we experimented with a number of different solvers, including IPOpt, HSL, MA86, Pardisu, Garobi, CBC, Juniper, and Bonwin. And this brings us to the third part, what I mean by under environmental uncertainty. So when we're designing a public health intervention such as genetic biocontrol, we're trying to use the best of our current knowledge about the dynamics of that technology that we're using, as well as the biology of that species that we're targeting, in addition to the environment in which it's all being deployed to make a decision. But each of these areas, as well as many others that I'm not explicitly referencing, carry uncertainties. Those uncertainties interact, and that can lead to a variety of possible outcomes from a single initial decision. So this decision tree is just to illustrate how, looking further and further into the future, the uncertainty within our system can increase. So work that co-authors and I currently have just submitted begins to address a subset of this uncertainty for the genetic biocontrol problem. And that subset is the environmental component. It's essential because it's a factor that's disproportionately complicating the human health question today, and it's climate change. And this goes beyond the rising averages that are shifting sort of the dengue appearance to increasing temperature variability. And that means that projected extremes or heat waves are getting larger in frequency and intensity. So the very hot days that might have occurred a single time in a decade could potentially occur 9 times while also being 5 degrees hotter. And that's to say nothing of the 50-year events, which heat extremes could be nearly 40 times more likely to occur. So temperature variability is an important part of the story in infectious disease ecology, but it's far less frequently examined in impact studies than temperature trends are, and it had yet to be incorporated into the literature that considers operational implications. And that's a critical gap because temperature variability is not just a problem of the future, right? Like I think many of us, hailing from around the world have seen even in the last several weeks, it's already a problem of the present. We had a discussion about this at lunch. So given the fact that daily weather uncertainty already does impact short-term operational planning in public health, including genetic biocontrol, the question is what happens when we can account for a range of potential weather manifestations in our optimizations. Can we make biocontrol deployment and the human health risk reduction that it enables more robust to uncertainty? So we test this by adding complexity to our current deterministic jump model, and we develop a 2-stage stochastic formulation of the problem, and then we compare the deployment strategies that are produced using the deterministic versus the stochastic models by simulating them. And this requires significantly building out our approach to data inputs and brings me to another area where JUMP has furnished critical capabilities from my work in disease ecology. Just from a basic starting point, the extensive community support and the online resources has been invaluable. And to my point about augmenting the complexity of our research question, to account for temperature variability. The documentation, I think this page has been cited like 6 times already today. So thank you, Oscar, and whoever else was involved. But on the documentation on design patterns for larger models was an excellent guide in developing better data structures and configuring them via Julia's multiple dispatch functionality. And I'll also say it's been really gratifying just how productive direct outreach to members of the JUMP developer community has been in answering questions and moving ahead with this work. So to very briefly highlight some results from that application case, what we found is that there is indeed a discrepancy between deployment strategies that are recommended by the deterministic versus the stochastic optimization models, that this difference is more significant given assumptions of future temperature variability, but it is also present given historical temperature records. So Here we have results in the lighter color is the deterministic release schedule for the historical period of the early 2000s. And so again, population size, the releases that we're conducting is on the y-axis, and then the time over a year is on the x-axis. And 45% of resources were saved when we accounted for uncertainty in the historical case. But in the stochastic case, again, with the lighter color being the deterministic and the darker color being the stochastic, here I'm looking at temperatures that were simulated for the 2030s, so that's what I'm categorizing as the future here. And we see a 284% savings in resources. And when I say resources, I mean that the accounting for the labor of like going out to the field and making the deployments, in addition to the materials that have been used, so like the actual organisms that had to be developed. So the intuition here is that because we're likely to encounter a wider range of variation in temperature going forward, where we know that temperature is extremely relevant to the thermal biology of those vectors that we're targeting, the ability to optimize over uncertain environmental scenarios will become more and more important in the future as we seek to efficiently and effectively deploy genetic biocontrol. So in closing, I mentioned that this was like a fairly new set of methods in this area. So I formalized them into the optimization tools into a software package. And the objective is to just make them a bit more accessible to those who actually do plan public health interventions and experimental field deployments. So the optimization features are enabled by JUMP. So this is contained within a larger library in which the deployment strategies that are put by the optimization can be tested under alternative climatic scenarios. And in turn, if the planners kind of want to do the traditional simulations and kind of just understand what the effects of a schedule are under different climatic scenarios, they can use the dynamic part of the model, which is built on top of differential equations. So with that, I'll reiterate thank you to the JUMP community as a whole. It's been a great experience, and it's really made this work possible, so I appreciate it.